Well, hi everyone. Welcome to my video about Higgs boson. If you were ever wondering about Higgs boson or just bored enough wanting to know about it, you are at the right place. I'm going to talk about very basic information about Higgs boson and its discovery. Towards the end of the video, I'll talk about a speculation about its unstable mass value. Before we jump into the topic, let me introduce to you something. Particle physics. Particle physics is nothing new, although in a sense of having mathematics as the basis is not too old. We had numerous philosophers even before the Greeks in places like in modern-day Turkey. Thales, Anaximander, Anaximenes, who taught of ideas that nature is made up of elementary building blocks, influenced many philosophers. Then we have Greeks as well, like Empedocles, Parmenides, and Democritus, who took it even further to influence and develop the idea of natural elements. We can fast forward our time to Isaac Newton and James Clerk Maxwell, and of course, a person like Einstein. We had numerous thinkers and scientists that led us to develop the concept of particle physics. Going back, Democritus gave us good insight into something. He came up with the term atom. Basically, he thought that the world was made up of atoms, which are, in his definition, indestructible, indivisible, and invisible. Democritus said that they are very small and homogeneous as well, and the atoms have all different kinds of shapes and sizes. Imagine a spherical atom. Democritus thought that liquids could have been round shape, or solids are something pointy. It could be this shape or that shape that can make up what we see and feel. But it's not the atom that we know of in modern times. For Democritus, an atom was something that cannot be divided any further. But atom that we know of today can be identified by proton, neutron, and electron. We have Isaac Newton, who thought that the world and vacuum was filled with something called ether. It can be spelled this way or just use this word instead. But basically, Newton thought that ether was necessary to exist in order for light particles to be transferred or in order for gravity to work. Einstein was the one who said that there is no need for ether in order for gravity and light to behave as it is. But even Einstein was curious about other possible subatomic particles. Through numerous physicists, particle physics have developed something in early 1970s, what we know now as the Standard Model. All the boxes that you see are the subatomic elementary particles that we know of. By the way, Standard Model is currently the best explanation of particle physics today. It's not considered something foundational, but as a best explanation that we have available. There are still tons of questions unanswered, but anyways, on the left hand side, the pink and green boxes are categorized as fermion. They are the ones that make up basically the materials and objects that we can see and touch, or just any materials basically. The pink boxes are called quarks. They have names like up, down, charm, strange, top, and bottom. Quarks are the ones that make up the famous proton and neutron. For example, the up quark and another up quark and a down quark make up a proton, and an up quark, down quark, and another down quark make up a neutron. We see the green boxes, which are called leptons, and most famous lepton that we know of is electron. Besides that, we have muon, tau, neutrino electron, neutrino muon, and neutrino tau. On the right hand side, the red and yellow box we see are categorized as boson. They are the elementary particles that carry forces, and out of those bosons, the red ones are called gauge boson. Gluon is the particle, a strong force, that holds the quarks together to make up proton and neutron. Photon is light particle, and we have weak forces like W and Z boson. Now finally we have something called scalar boson, the yellow box, which is the Higgs boson. So now we are getting to talk about what it does and what it is. So let me tell you first the problem and why we need Higgs boson. As you look in the table on top, there are numbers. They represent their mass, but here's the problem. Previously, when physicists were using quantum field theory, they are supposed to be massless, right? Let's take an example. You have a top quark and an electron. Both particles behave differently as if they have mass. Top quark, as we found out later, has massive mass compared to electron. Top quark has actually a mass that is almost as heavy as atomic mass of gold. But guess what? They are both about the same size. If they are both massless, they should be moving at a speed of light. Speaking of light, we have photon with mass of 0. Because of that, it makes sense that the speed particle, the photon moves at speed of light. I hope you get the idea. Higgs boson is an elementary particle that gives mass to other subatomic particles. To give you an illustration of how it works, let's think of water. There are animals that can move fast, and we have animals that move slower in the water. Similarly, for fishes that live in water, we have Higgs boson that is filling up the whole universe and atmosphere and wherever we are. And the water molecule and Higgs boson will act similarly if we think in terms of moving through the space. Think of a particle in space filled with Higgs boson, which it is. That's where the term Higgs field comes from. Some particles will interact more with the Higgs field, and some don't. Through the interaction between a particle and a Higgs field, an internal energy is created which gives mass to the particle. Just think of E equals mc squared. The higher the energy, the higher the mass. So now you have the basic idea of what Higgs boson does and the general picture of standard model. The Higgs mechanics is also called the Brout, Englert, Higgs, Gerlach, Hagen, Kibble mechanism. Those names are the names of 6 people who came up with the concept of Higgs mechanism around the same time, which was 1964. Actually, to be exact, 1964 is when Peter Higgs proposed the idea of Higgs mechanism. But anyways, most of the credit goes to Peter Higgs, as we see that the boson is named after him. Maybe you guys want to see more professional picture of him, but anyways, when it was first proposed, Peter was received with many opposition and critiques, but at the end he received Nobel Prize in December of 2013, along with Englert, but without his partner Brout because he passed away before the discovery of Higgs boson. The reason Englert and Peter was able to receive this great award is because of its discovery. When and where was it discovered? It was discovered in July 4th of 2012 in good old Switzerland, known for Swiss cheese, Swiss chocolate, and Swiss watch. And also an European research organization called European Organization for Nuclear Research. It is also called CERN for short. This organization is worldwide respected for their scientific research facility and its members from all around the world. They use something called a particle accelerator, the name Large Hadron Collider. Large Hadron Collider is basically a gigantic instrument that accelerates 2 particles, such as proton, and let them collide each other. Large Hadron Collider was built through a collaboration of more than 10,000 scientists and engineers from over 100 countries. It has a shape of a circular ring underground 27 kilometers long. This gigantic thing is able to speed up the particles that travel in opposite direction up to very close to speed of light. Tubes kept at ultra-high vacuum guided by superconducting electromagnets that are chilled down to negative 271.3 Celsius for minimum resistance and loss of energy. There are 1,232 dipole magnets that are 15 meters long, bending around the beams, and other 392 quadrupole magnets that are 5 to 7 meters long for beams. If you look at the picture, ignoring all other stuff, you see the circular ring, and you can see names on the picture along the ring. Those are the names for detectors. One of the detector that was used to observe Higgs boson was ATLAS. It's spelled all capital ATLAS. Do you see the little guy in the bottom middle? Yeah, the detector itself is also ginormous. This thing also requires collaboration of over 3,000 physicists. So the tube goes through the detector and the particles actually collide in the tube where the detector is, and the detector is able to observe and record the collision of particles. When the particles collided and Higgs boson was observed, it looked something like this. If you're a person that prefers 3D, all those lines and things you see is a result of the collision. I will explain about that very little at the very end of this video. But yeah, this was the basic story behind Higgs boson and its function. Of course, I'm not done yet, since I told you guys that I'll be talking about Higgs mass. When CERN observed the collision, they estimated it to be around 126 GeV. Some sources say 125, but I'm going to stick with 126 since a physicist from CERN has given a presentation about it as 126. Anyways, 126 GeV is very heavy for an elementary particle. This is the same mass as a substituent of DNA, thymine. So hear me out why the mass plays such important role. Universe. Our universe can exist in an excited state where it's not stable. The state our universe depends on the potential of Higgs field, which really depends on the mass of Higgs boson. I personally don't know any mathematics behind it, but the potential of Higgs determines what state our universe is in. The stable state of universe would be the ground state, or we want to be in a true vacuum. If the universe is not at the true vacuum, not a ground state, our universe naturally want to shift to the ground state, just like the one on the table wanting to go down on the floor to feel safer. If we look at the graph, you can see two dips. This would be the ground state, or the true vacuum, and this would be not. That would be a local vacuum. If our universe was in this state, our universe would stay as it is, but we are in this state, our universe would want to shift down to the stable state. This shift is called quantum tunneling. What is quantum tunneling? Well, let's imagine a guy next to a house. If this guy suddenly appears on the other side of the house, that is quantum tunneling. There are many great videos out there about quantum tunneling, so if you don't understand, you can pause the video and look it up. The probability of a person doing that is almost zero, but at subatomic level it happens all the time. Although this picture is very misleading, imagine our universe going through a phase transition. It's like the different state between frozen state and liquid state. So if we are currently living in a local vacuum, we will get to experience that kind of phase transition. And theoretical physicists have figured out two different states that Higgs boson can exist. The one top left is the picture of the Higgs field density in which we live in. This is not actual scale, so let's just imagine that it is. On the bottom right, the picture represents the ultra-dense Higgs field, and actually the ultra-dense Higgs field, that state is billion upon billion times denser than the current one. If our current Higgs field was a little bit denser, our atoms that we know of would change drastically. The nucleus wouldn't be able to hold on together, and we would have only hydrogen in the universe. But imagine what it would be like at ultra dense state. There would be no life form whatsoever, and the chemistry we know of today wouldn't exist. And how does quantum tunneling happen? Well, let's imagine water on a stove. As water starts to boil, bubbles are created. Similarly, it is possible for a bubble of ultra-dense state of Higgs field to appear in the universe, expanding in speed of light. But even if it were so, we don't have to worry about it since we were safe past billions of years, so it probably won't happen anytime soon. Either our sun will swallow us first, or thanks to dark energy being pumped into our universe, we will travel faster than speed of light away from ultra-dense state because of the expansion of the universe. Or it might just not happen. Then again, if it happens, it is also possible for our whole universe to transition all at once into ultra-dense state. But if we think about how the mass is observed in the first place, we have to remind ourselves. The particle accelerator creates such high velocity to create such powerful energy when it is controlled in order to observe Higgs boson. This means that the Higgs is in an excited state thanks to the accelerator. So we may be completely wrong about this whole thing. Just one more fun fact. We actually never really observe Higgs boson, or have we ever observed Higgs boson? When the particles collide, because of the high velocity, it quote quote slaps the air. The slapping of the air is what we are observing in the previous picture. The different elementary particles are created, and this observation is a perfect explanation for existence of Higgs boson. They are going to be impossible to observe anyway, since they live about 1.6 times 10 to the negative 22 seconds. They all go through something called Higgs decay, meaning they become other elementary particles, but that's a story for another time. Here are some people that helped me to understand about this topic. They have videos as well as TED Talk. I also recommend to read a book called The God Particle by Leon Lederman, an experimental particle physicist famous for Nobel Prize on study on neutrinos. One thing you have to keep in mind is that his book was published in 1993, way before observation of Higgs boson. But anyway, thanks for bearing with me. I hope that this video helped you, or at least answered some of the questions you had. Well, thank you for watching, and feel free to leave a comment or question, which most likely I will not be able to answer. But, well, bye.